Right, so welcome everyone to the Schubert seminar. We're happy to start the spring semester with a new series of lectures. And today we're happy to have Yuxiang Liu from BIMSA telling us about rigidity of Schubert classes. So please take it away, Yuxiang.
Thanks. Thank you for the introduction. I'm going to talk about the rigidity of Schubert classes. The key question of this talk will be the following. We consider a rational homogeneous variety X, where G is a reductive group and P is a parabolic. Then we take a subvariety Y of X. It is known that the Schubert classes form a basis of the cohomology. So we can write the cohomology class of Y as a linear combination of Schubert classes. Then we ask what properties of Y are determined by its cohomology class. For example, if the class of Y is a Schubert class, then we can ask whether Y has to be a Schubert variety. If the answer is positive, then we call it rigid. And similarly, if the class of Y is a multiple of the Schubert class, then of course one possibility is that Y is a union of Schubert varieties. If it's the only possibility, then we call it multi-rigid. And during this talk, I will discuss this problem in three settings. First, in the Grassmannians of type A, it is a simplest case. And then we'll talk about the partial flower varieties of type A, which is a generalization of Grassmannians. And we will make use of some rigidity result from Grassmannians for this case. And last, I will discuss some methods that can be used for some Grassmannians, which is of type B or type D, depending on whether n is odd or even. So first, the Grassmannian case, let our X to be the Grassmannian variety JKn that parameterizes all k-points in n space. Here we fix a complex vector space V of dimension n. The Schubert varieties are defined using a reference flock F as well as an index. Here we use a strictly increasing sequence A1 to AK to indicate the dimension of the flock elements. So FAI is a subspace of dimension AI. Now, given a reference flock, the corresponding Schubert variety consists of all the k-points that meets FAI in dimension at least I. Okay. Then we take a subvariety Y of X, and we write its class as a linear combination of Schubert classes. Then we can consider the instant correspondence of a point in a k-plane for k-plane in Y. It maps onto Y under the second projection, and we let phi to be its image under the first projection. Then the observation is that the dimension of phi is determined by the class of Y. The dimension of phi equals the maximum of AK minus 1 among the summands in the class of Y. The proof is straightforward. We take a subspace gamma in general position, and we consider the locals of all k-planes that meets this gamma in dimension at least 1. This sigma is in fact a Schubert variety, and its class is the so-called special Schubert class, which means we can make use of Pure's formula. By Pure's formula, the intersection product of y and sigma is 0 if and only if the dimension of gamma is less or equal to n minus the maximum of ak. And on the other hand, we know that the intersection of y with sigma is empty if and only if the variety phi y does not meet the linear space gamma. Recall that this phi is a variety swept out by the projective linear spaces parameterized by y. And these two conditions combine together to get the dimension of phi equals the maximum of ak minus 1. Now we know the dimension of phi. We may ask, what's the shape of this phi? What's the degree of it? For the next proposition, we assume y is irreducible, and therefore phi y is also irreducible. If the maximum of ak minus the maximum of ak minus 1 equals 1, then phi y has to be a linear space. To prove it, we take a general point P in phi, and we consider the sublocals of all k-planes in y that contains this point. To compute this class, we take our gamma again to be a subspace in general position, and here we require the dimension equals n minus the maximum of ak plus 1. So gamma is of the minimal dimension so that the intersection product is non-zero. And under this condition, phi y would meet the linear space gamma in finitely many points. The number is given by the degree of phi. And thus at each point, the class of yp is given by the intersection product divided by the degree, the number of points. If we write its class as a linear combination of Schubert classes, and in fact we can compute it using the Pure's formula, we get the maximum of bk equals the maximum of ak minus 1 plus 1, which is, by assumption, the maximum of ak.
So I'm a little confused. What is the maximum of ak minus 1? What does it mean? How is that different from the maximum of ak?
So it is from our definitions. Our ak is the largest subindex, and ak minus 1 is the second largest subindex in the sequence. And here, for maximum ak, we take the maximum on all the summand in the class of y.
Oh, I see. Okay, thank you.
Yeah. And same for the maximum of ak minus 1. We take the maximum of ak minus 1 among all the summand in the class of y. And this condition in the statement implies the maximum of bk. Here, for bk, we take the maximum among the summand in the class of these sublocals yp. We get the maximum of bk equals the maximum of ak. Then we can use the same argument on the above to find the dimension of phi with respect to these sublocals. So this phi of yp is a variety swept out by the projective linear spaces parameterized by these sublocals yp. We get this dimension equals the maximum of bk minus 1, which is same as the maximum of ak minus 1 equals the dimension of phi y. Also, by assumption, our y is irreducible, and therefore this fiber is also irreducible by the fiber dimension theorem. And thus we can conclude the equality phi y equals is phi yp. Also note that for every k-prime in Y that contains this point P, this k-prime must be contained in the tangent space of phi at this point. And that implies phi y is contained in its tangent space at this point. And therefore, we can conclude that phi y must be a linear space. And in particular, if Y is irreducible and the class of Y is a multiple of a Schubert class, then if AK minus 1 equals 1, there exists a subspace of dimension AK that contains all the k-prime in Y. It is just a translation of the previous proposition. And it just means, and we can also see that the dimension of the intersection of lambda and FAK is at least k. Then we can ask whether similar properties hold for the other subindices. And that leads to the following definitions. A subindex is called essential if this condition holds. If a subindex is not essential, that just means we can safely ignore the inequalities involving FAI in the definition of Schubert varieties, and that would result in the same locals. And in particular, the largest subindex AK is always essential. A subindex is called rigid if for every representative, we can find a subspace of dimension AI that meets all the k-primes in Y in dimension at least I. It is called multi-rigid if for every irreducible representative for multiple of the Schubert class, we can find a subspace of dimension AI that meets all points in Y in the correct dimension. The next theorem allows us to reduce the rigidity problem for Schubert classes to the rigidity problem for subindices. A Schubert class is rigid or multi-rigid if and only if all essential subindices are rigid and multi-rigid. One direction is trivial. If a Schubert class is rigid or multi-rigid, that means a representative Y must be a Schubert variety. And therefore, we can find the defining flag, and for all the subspaces correspond to the essential subindices, we have the inequalities on the dimension on intersections. And conversely, if all essential subindices are rigid or multi-rigid, then we have a set of subspaces corresponding to the essential subindices. Then one can prove that the subspaces in this set form a partial flag. Then we can use this partial flag to define a Schubert variety which is of the same dimension of Y. Since Schubert varieties are all irreducible, we conclude the equality between Y and the Schubert variety. Okay. The next way can classify the rigid and multi-rigid subindices of Grassmannians. A subindex is rigid if and only if one of these two conditions holds. And if both conditions hold, then AI is also multi-rigid. Clearly, the multi-rigidity is a stronger version than rigidity. For proof, we take a representative Y, which is an irreducible subvariety whose class is given by a multiple of sigma A. The first step is to prove that if the second condition holds, we can find a projective variety phi of dimension A minus 1 that meets all points in Y in the correct dimension. It can be proved by induction. We just take a general hyperplane and we count everything done by this hyperplane. We consider the sublocals of Y of k-planes that contains in this hyperplane. Then we can use induction on dimension. The second step is to prove if either m equals 1, the coefficient equals 1, or the first condition holds, then phi from the first step has to be a linear space. If m equals 1, then we can intersect this phi with a general linear space of complementary dimension. And if the intersection consists of more than one point, one can argue that there's a contradiction on the class. And if this condition holds ai minus 1 plus 1 equals ai, then one can argue that we can pick a general point of phi, and consider the sublocals of k-planes that passing through this point. Using the argument from step 1, we can find the same, we can say we will have the same phi for these sublocals. And that would lead to the condition that phi I is contained in the tangent space of phi at this point, and therefore phi has to be a linear space. Okay, next I would like to talk about the class of the case of partial flower varieties. I think maybe it's a good time for a break.
All right, so maybe let's take a 5 minutes break. So we'll be back at, let's do 4:55, so 6 minutes break.
Okay.